everyone, my name is Dennis Federation and I'm here to present our paper called Hear the Flow, Optical Flow Based Self-Supervised Visual Sound Source Localization. And so visual sound source localization, it's essentially given a video, can you localize the dominant sounding object or objects in the video? So whether it's vacuum cleaners or a person playing the accordion, can you localize where the sound is coming from in that video? And we can easily train a supervised method to do this, but it would require some very expensive bounding boxes to be labeled manually. And so the question is, can we do this in a self-supervised manner? And as we know, building strong self-supervised models is a challenging task. But this paper, we're working off of previous works in a complementary way in that recent works create new loss formulations for improving contrast representation learning for this task. But we look at it in a different angle in that we are looking at informative priors to aid in the localization process. And so what I mean by that, for an example, is oftentimes the objects in a video that are moving are actually the ones making the sound. And so we model that characteristic using optical flow, and we show that it significantly improves localization capabilities. And so first I'll show how localization works, and then we will add optical flow in at the end. So the way it works is, given an image frame of the video with audio surrounding that frame, we extract features from both, and we get the global audio features, and we do a cosine similarity of the audio to every spatial location of the visual features. And this similarity measure becomes the heat map, where areas of high similarity are where we localize towards. And to train this in a self-supervised fashion, we create two positive and negative pseudo-masks. Essentially, we're thresholding this heat map, and then we aggregate these positive and negative responses, very similar to what we see in many contrastive learning methods. And then we train this with loss resembling influency, again, very common in the self-supervised learning space. And now when we add optical flow, we follow almost like a self-attention operation that you see in transformer architectures, where we're actually doing a cross-attention, where we use features from optical flow that are extracted and the visual features to create an attended version of both. And so we create a cross-attention matrix of flow and visual feature representations, and then we can construct the final cross-attended optical flow feature or prior. And then we add it back into the original visual features and construct an enhanced similarity matrix or a localization map with these enhanced features that had optical flow attended in them. And when we do this, we actually see state-of-the-art performance on all of the benchmarks in visual sound source localization, and by a pretty significant margin, in some cases 5 to 10% improvement. And we see a further improvement in cross dataset generalization experiments and when we test on unheard sound classes. And when we actually look at example results, we see that with the addition of optical flow, we can see how the model is actually using them to localize better. So these are a few examples of, for example, a car moving or a person talking, where they're exhibiting movement, and they're also the ones generating the sound. And the model can use these optical flow features to better attend and better localize to where it's coming from. And given the cross-attention architecture of our network, this model also performs well when there actually isn't any meaningful optical flow, and it outperforms previous methods in this regard as well. And so overall, in this paper, which we encourage anyone interested to read further, we use the idea of informative priors to improve the training of self-supervised visual sound source localization models. And specifically, we create this optical flow localization network that achieves state-of-the-art performance. Thank you.